Hi everybody. Today we're going to be looking at the chain rule, section 14.5. Now, when we're looking at this chain rule, we're going to have to go ahead and revert back to this idea of this total differential that we saw in the previous section. So, when we look at this total differential, we had something that looks like this. This was that total differential that we were looking at. Now, in this particular section, we then want to start analyzing this a little bit further, and we now want to figure out, or we now want to talk about, what would happen if we start using a parameter t. So, taking into consideration what we're looking at here, that the total differential is, once again, written by this particular equation, what we can do now is we're going to work with the differential, and we're going to divide by the differential with respect to t on both sides. Now, naturally, when that happens, we get to this point that says that the differential for the function z with respect to t now looks like this. And the reason we want to do this is because now we can start saying, hey, our function for z, the function that we originally started observing, f of xy, can now be composed of different or a different parameter. Call it t. All right. Now, we have a general case for this chain rule, and I'm going to write the general case for the chain rule down below. All right, so here's a definition that we use. We're going to say, suppose that we have this function of two variables, which we'll call z, and that function is a differentiable function of x and y, meaning we can take the derivative both with respect to x and with respect to y. Now, x is going to be parameterized by s and t, and y will then be parameterized by s and t as well. When this happens, we can then look at the total differential of that function. And using that total differential, we're going to be applying what is known as the chain rule. So here's where we have this chain rule occurring. All right. Now, how is this going to look like? So let's look at an example. If z is equal to x squared y plus 3x y to the fourth, where x is equal to sine of 2t and y is equal to cosine of t, we want to find the partial of z, we want to find the differential for z with respect to t when t is equal to 0. So, using the process that we saw above, from above, we should get something along the lines of this, that when we're looking at the total differential here, dz dt, this is going to be the partial of the function with respect to x multiplied by, we could say the partial with respect to t, but since this function and this function only have one variable, it's not really a partial derivative. It's still going to be a derivative from Calc 1. Which means that this is just going to be the derivative of x with respect to t plus the partial of the function with respect to y multiplied by the derivative of y with respect to t. So we got a few things that we need to do. First, we're going to figure out what the partial of the function is with respect to x. And let's work on that. So the partial of the function with respect to x, that's going to be 2xy plus 3y to the fourth. We also need the partial of z with respect to y. That's going to be x squared plus 12x y cubed. Good. Now we're also going to need the the derivative of x with respect to t. And that's going to be 2 cosine of 2t. And we also need the derivative of y with respect to t, and that should be negative sine t. There we are. Perfect. So now that we have all of these derivatives in play, we can now go through and we can now start using our substitutions. All right. So coming over here to the total differential, let's split this here. Here we go. So the total differential that we're going to look at for the function with respect to t is going to be the partial of f with respect to x, and that's going to be 2xy plus 3y to the fourth multiplied by the derivative of x with respect to t. That's 2 cosine of 2t plus partial of the function with respect to y. That was x squared plus 12x cubed, xy cubed, multiplied by the partial or the derivative of y with respect to t, which is negative sine t. Now, if you notice that at our derivative is mixed here. It has cosines, it has t's, it has x's, and it has y's, which means we need to go back through and we need to evaluate when is x given a value when t is equal to 0, or in other words, what value is t or is x when t is equal to 0. So we need to find those values. So let's go through and do some work here. Alright, so x at 0, because that's going to be t is equal to 0, this is going to be sine at 2 times 0, which will be 0, and then y at 0 is going to be cosine at 0, which is 1. So when we're considering t is equal to 0, all we have to do is check these x values or y values that were given. So coming over here, this derivative or this differential for z with respect to t, we're now going to evaluate this when t is equal to 0. Using this evaluation, we're then just going to make our substitutions. 2 times y, 2 times x and y, x was 0, y was 1, plus 3 times 1 to the fourth, times 2 times cosine of 2 times 0, plus 0 squared, plus 12 times 0 times 0, times 1 cubed, times negative sine of 0. Alright, we can go through and we can evaluate this. Let's go ahead and see what's going to cancel out or go away. Alright, that's going to go away. That's a 0. Alright, that's going to be a 2. That's fine. So that's a 0. That's a 0. That's a 0. So all of this zeroes out. That's nice. Which means all we're left with is 3 times 2, which in this case is 6. And that's our final answer. So when we're working with these chain rule derivatives, we have to make sure that we account for all of the variables that are occurring. Now, we usually use what is known as a tree diagram in order to generalize this a little bit more. So I'm going to say here that this is going to be the tree diagram. Oops, excuse me there. I'm going to say that this is going to be the tree diagram for the chain rule. Alright, and then we're going to let a certain function occur. That way we can see what the differentials are going to be. Alright, so here I'm going to have my function, let's call this w, is going to equal to my function f of x, y, z, and t. And I'm further going to define that x is going to be some function that contains u, v. Y is going to be some y function that contains u, v. Z is going to be some function that contains u, v. And t is going to be some function that contains u, v. Alright. So notice there's a lot of embedding taking place here. And the embedding is happening when we're considering that x here is going to contain two variables, y is also going to contain two variables, z contains two variables, and t contains two variables. And what we want to use this tree diagram for is to illustrate what the total differential is going to be. In other words, we need to account for all of the partial derivatives of all of these nested functions.
What?
So let's go with the tree diagram. So the tree diagram is going to start with the function that you're observing. Alright, so here we're going to have w. That's the function that we start with. W is then broken up into smaller functions. W is made up of x, y, z, and t. So this is where we then input x, y, z, and t. Now, x is then broken down into u and v, which means x contains u and it contains v. Y contains u and it contains v. Z contains u and it contains v, and t contains u and it contains v. Now notice this is why we call this a tree diagram, because it kind of looks like it's a tree just branching out. Now all of these variables have these different names. Alright, so w here, this is known as your dependent variable. X, Y, Z, and T are known as your intermediate variables. Oops. And finally, U and V are known as your independent variables. So, how does this help us figuring out the total differential? Well, the way this is going to work is, what if we had a question that said, find the partial of w with respect to, let's say, u. Well, we would then have to go through and we would then have to try to figure out how we're going to be able to work this. Let me put this here. we'd go through and we'd have to figure out how we're going to work this to make sure that we find this total differential just based off of the given information. So here's how this works. Oops. Excuse me here. The partial of w with respect to u. Wow, technical difficulties in the morning. It's okay. So here we go. I'm going to write this in purple. And what I want at this point in time is I want the partial of this u, of this u, of this u, and of this u. Alright, so I need to make sure I get to those u's. And getting to those u's is going to follow by following the path of the branches. So the first path that we're going to start off is from w to x. This means that we're going to take the partial derivative of w with respect to x. The next path that we take then is going to be the path that goes from x to u, because again we want that partial derivative to wind up with u. Alright, there we are. So that's one of the first ones. The next one, we're going to go down a second path. Going down a second path, now again we're trying to capture this u here in question, which means to get to that one we go through the partial of w with respect to y. That's the first branch. Second branch goes from y to u, which means this is partial of y with respect to u. We need to go down the third branch. Alright, so that's going to be partial of w with respect to z, and then the partial of z with respect to u. Going down the last branch to capture that last variable for u, it's partial of w with respect to t, and then partial of t with respect to u. Now that we have all of these partial derivatives, we're just going to go through and we're going to write them up. So the total differential for w with respect to u now turns to be, follow the first branch, partial of w with respect to x multiplied by the partial of x with respect to u. And that piece came from these two here. Oops, excuse me. Then plus, second branch, partial of w with respect to y times the partial of y with respect to u. And that one came from these two. Next one, plus third branch, partial of w with respect to z multiplied by the partial of z with respect to u. And again, that one came from here, that third branch. Excuse me. Last branch, partial of w with respect to t multiplied by the partial of t with respect to u. Alright, perfect, because that was that last branch, which means that comes from this piece. So anytime that we're asked to find a chain rule or to find the total differential for a certain function, and that function has compositions embedded into it, then we have to go through and we have to use this tree diagram to find out what are those differentials that we need to account for. Now, there could be a separate question here. The separate question could also be to find the partial of w with respect to v. So if I were to ask you this question on an exam, given all of this information right up here, could you then draw the tree diagram, and could you then write out this total differential for this given derivative? Now I'm going to leave that up to you. So really quickly pause the video and see if you can extract that total differential, and I'll go ahead and write out the answer in just a bit. So if you want to pause the video now, go ahead and do it. Alright, great. So now that we have this process for differentials or for chain rule, what I want to work on next is going to be kind of like a problem that we saw in one of the previous sections. All right, so excuse me really quick. The problem that I want to look at was for the previous section, section 14.4, when we were dealing with partial derivatives. Now, when we were dealing with partial derivatives, at the very end, we were asked to find a implicit or find an implicit differential. All right. Now, when we found that implicit derivative, there was some time that took us to be able to generate that derivative, and we had to figure out what was that process back from Calc 1. All right, so in here we're actually going to streamline this process just a little bit more to see if we can get the desired result that we need. All right, so really quickly, I'm going to start this by saying, let's do this in, oh gosh, I don't know. Let's do this in, let's say this purple. Or purple, pink, whatever this may be. All right, so here we go. Let z equal to f of xy. So again, z is going to be classified as this two-variable function. And the next thing I'm going to do is I'm going to say, so z minus f of xy is equal to 0. All right, I just subtracted one side to the other. Okay, not so bad. Now I'm going to define a new function. So I'm going to define my function, capital F, as x, y, and z. And this function of x, y, z is actually going to be equal to the function right above that we had previously defined. It has some z coordinate, and then this function f is going to contribute the x and y to it. All right, so got all this going for us. Great. So we have this three-variable function at this point in time. So what I want to do really quickly is I now want to calculate the total differential for this function, or in other words, I need to calculate that using the chain rule. So what I want to do here is I want to find the partial derivative of the function with respect to x. All right, so we're going to go through that. That's going to be equal to partial derivative of the function with respect to x multiplied by the partial derivative of x with respect to x plus partial derivative of the function with respect to this case y multiplied by the partial of y with respect to x plus partial derivative of the function with respect to z multiplied by the partial derivative of z with respect to x. Awesome. Now, we have all of this ready for us, but there's a few things that are not working out here as great as we'd like them to. Now, the things that are not working out as great as we'd like them to, or let's say that they are working out to our advantage, we're going to say this. I'm going to say, oh, excuse me. I actually want to use the same color. Sorry about that. I don't know what I was thinking there. So, I would say, but wait. But isn't the partial of x with respect to x just 1? Since we're taking the derivative of x with respect to x, should just be 1. And the partial of y with respect to x. Well, remember how we defined these branches here? The final branch down here is your independent variable. This means that as we're looking at this, x and y here were independent variables, so that means that y cannot have some variable of x embedded in it. Therefore, when I take the derivative of y with respect to x, it's a constant, which means that derivative is 0. And we got one more. The partial of the big function with respect to x. This is actually equal to something. Now, remember how we defined this. This function was here. but that function is equal to 0. So what happens when I take the derivative of the function with respect to x if that initial function is equal to 0? Well, you guessed it, we get 0. All right, derivative of a constant gets a 0. So using all of this, I'm going to resubstitute into what I have here. So this means that my partial of f with respect to x is 0. Partial of f with respect to x, that's going to be multiplied by 1, plus partial of f with respect to y, that's going to be multiplied by 0. And then finally we have the partial of capital F with respect to z multiplied by the partial of z with respect to x. Now looking at this here, doesn't look quite nice, but it's actually really, really beautiful, because what we have here is a key. And we have a key that's going to open up this door that's going to lead us back into section 14.4, which is what we were looking at when we were talking about partial derivatives. All right, let's keep going here. We're almost there. We're almost there. There we are. And finally, I want to solve for the partial of z with respect to x. There we are. That is the function that we want. Believe it or not, this is the key to working with section 14.4. Now, why is that the key for working with section, or for working within section 14.4 when we're talking about implicit differentiation? Well, let's rewrite this really quickly. Could I rewrite this in this form, that the partial of z with respect to x is equal to negative partial of this function, capital F, with respect to x, divided by capital function derivative with respect to z? Sure, that's exactly it. It's still the exact same value. Now, this is where it gets interesting, because again, the way that we defined that the partial of z was equal to x was by creating this new function. So, using this newfound process, we're going to go through and we're going to find that derivative, or that partial derivative, that we were looking at in the previous section, right at the end of the last section. So we want to find the partial of z with respect to x for this function. X cubed z squared minus 5xy to the fifth z is equal to x squared plus y cubed. Now, spoiler alert, you already know the answer to this, because again, we did it in the previous section. But we want to reapproach it now with this newfound method. All right, so instead of doing this implicitly, can we then use this process up here? All right, well, sure, let's see if it's going to get us the same answer. All right, so the first thing I'm going to do is I'm going to define a new function. So I'm going to say here, let's say x cubed z squared minus 5x y to the fifth z minus x squared minus y cubed equal to 0, or in this case, this is going to be my function f of x, y, z. All I need to do now is find two partial derivatives. The first partial derivative that we need to find is going to be the partial derivative with respect to x. And since this function here only has x, y, and z embedded into it, all we need to do is treat the y's and the z's as constants when I'm looking for this derivative. So derivative of x cubed, that's going to be 3x squared, z squared. Derivative here, minus 5y to the 5th z. Derivative here, 2x. That's it. Partial with respect to z for that function, again going through the same process. That's 2x cubed z minus 5x y to the 5th. And I believe that's it. So when we want to find this derivative, the partial of z with respect to x, all we need to do is take negative the partial with respect to x and then divide by the partial with respect to z. Let's see if that's true. All right, partial with respect to x, remember the negative. And this is going to be 3x squared z squared minus 5y to the 5th z minus 2x, all divided by partial with respect to z, which is 2x cubed z minus 5xy to the 5th. So you can double check this. If you distribute the negative into that numerator, we get the exact same answer as the previous section. So we get the same answer as section 14.4. Which is really, really cool because, again, now this streamlines the whole process of taking a derivative implicitly. We no longer need to take the derivative implicitly if we know how to account for this change. All right? So we could keep using this rule or this process as much as we'd like. So what then would we do if we were to say find the partial of z with respect to x for the previous equation? Or you could say example. Well, that process again would then be nice because looking at the partial of z with respect to y in this particular case, wow, I'm so sorry, I put dz dx and that's supposed to be dz dy. There we go. Now that process would be very, very similar in a sense that we would still define a new function, except now we would say that the partial of the new function with respect to y would be, or sorry, the partial of z with respect to y would be equal to negative of the new function with respect to y divided by the new function with respect to z. And we would be able to work through that problem. So check it out. I want you to do that on your own, and I'm not going to release that answer unless I'm being asked to. All right, but I strongly encourage you all to try this, and I believe that you can all get to that answer. All right, now that's going to wrap it up for section 14.5, which is known as your chain rule.